All right, so now we know why you want to do a, like how to add a continuous predictor, and then in this case, how we're dealing with the CE sample. And now let's look at how we can set up the model for this case. So in SLR, simple linear regression for the CE sample, I'm using the notation in terms of 8 and 9. Equations 8 and 9, but this is really saying the same thing as before, and I provide the table of the description of the two variables that we're working with. And down in the remarks section, I just restate what it means to have the intercept and the slope in the context. So again, earlier I was saying, so first of all, yi is the log expenditure, xi is the log income. That's all fine. And the second bullet point in the remarks, I said earlier that sometimes xi equals to 0 is not meaningful in the context. For us, it's okay because we took the log in the first place. So if you have a 0 log income, that means your income is $1, right? Because you took the log. And so that you can still say that, okay, the intercept beta 0 is telling us the expected log expenditure mu I for this CUI who has 0 log income, which means they have $1 income last year. Okay? So again, I highlight those words because anything about beta 0 and beta 1, it's on the mean. Okay? It's never saying anything about the yi directly. It's only saying about the expected value of yi, which if you use the model specification equation 8 and 9, it will always be the mu I. Okay? So again, you might work in a different notation. I personally prefer writing this mu I, so I know this is the mean, and then how the beta 0 and beta 1 are affecting this mu I. All right, and then for the slope, well, if your log income increases by 1 unit, that means, because this is a natural log, right? So log increases by 1 unit, you can think of it as the income increases by what, 2.78-ish US dollars. Then beta 1 tells you the change in the expected log expenditure. Okay? So that's what it means. Okay. All right, so what we're going to cover to get started is a weakly informative prior. So this is very typically done in Bayesian linear regression that, well, if I have nothing, I have no idea about where those beta 0, beta 1, and sigma should be, I'm just going to give very, very, very weakly informative prior, meaning that I'm going to let the data decide whatever that will be. So we're going to start assuming independence. So remember, we have this triplet of the 3 parameters that we have in the model. So if you try to write the joint prior, it's going to be whatever is on the left-hand side of equation 10, right? We have the joint prior of beta 0, beta 1, and sigma. And for now, I'm doing it step by step. So first of all, we're assuming dependence between the regression coefficient and the standard deviation. So I break it into 2. The product, factorize it into the right-hand side. But pretty easily, if you work with, so the first bullet point here is working with the regression coefficients, and I'm further assuming independence between beta 0 and beta 1, so I can do equation 11, so further factorize it into the product of the univariate prior for beta 0 and univariate prior for beta 1. And then for each of them, I'm giving, right now, I'm writing in terms of equation 12 and 13 that beta 0 follows a normal, mu 0, S0, and then beta 1 follows a normal, mu 1, and S1. And you will see down here that I give, like say, a typical weakly informative prior is giving beta 0 and beta 1 a normal center as 0 and a super large variance, or a super large standard deviation in this case. Okay, so that is just saying that I don't really know where this beta 0 and beta 1 are. And I assume it's going to be around 0. So around 0, what it means, when beta 0 and beta 1 equals to 0, or center around 0 in terms of the prior, we're just saying that it can be, I mean, normal 0, 100 is really just anything on the real line in some sense. Okay, and center at 0 for the intercept. They're just sorry, for the intercept, which is beta 0. That is to say that a priori, I think the intercept is 0, sort of center around 0, I should say. Okay, with the possibility of going through the entire real line. The slope as well. I mean, a priori, I think there's no slope, or I should say center around 0. So meaning that like the log income wouldn't really affect it, or like affected on expectation with 0. But I'm giving it a large standard deviation. Okay? So it can't really be anywhere. So that's for beta 0 and beta 1. And the rest is for sigma. And sigma, again, if you don't really have any good idea, just give it an inverse gamma. I mean, 1 over sigma squared to be a gamma. And typically, you can give gamma 1, 1. So that we have seen it before, right? When you have a normal model, when you're working with the standard deviation parameter, we typically like turn it into the precision, which is 1 over sigma squared, right? And if you have not much information about it, you give it a weakly informative prior, which is gamma 1, 1. Okay, so you can see that the setup is not hard, and it sort of like works reasonably okay for most of the simple linear regression like application that you're interested in. Typically, I mean, if you think about it, this weakly informative prior, the joint prior in this way, is really just letting the data to decide where I should put my beta 0, beta 1, and sigma in the posterior. Okay? It's all going to be how the data are going to determine where they're going to go. Okay, because in the prior, it's very weakly informative. All right, so if you do that, okay. Well, you can still work out the sampling model, which is the joint likelihood that I write over here, which now I assume everybody feels very comfortable about. And as you can see that I haven't done much more simplification. One thing is because we're gonna rely on checks. Another thing is this starts to like become more complicated if you think about what's in the exponent, because now the mean is beta 0 plus beta 1 times xi, right? So if we start to try to expand that equation, I mean that square term, it's going to become very complicated in order to recognize whatever the full conditional posterior will be. So I'm just going to leave it like that. But you know, like you are able to write the joint likelihood because each observation independently follows a normal distribution with a specific mean and the same standard deviation. And then, of course, naturally, next step, if you try to get the joint posterior, you're getting the likelihood multiplied with the priors that we specify. Okay, so I put things together just for you to know that the model itself is still coming from the normal. Okay, and we know how to write the normal density. Okay, and you can still get them jointly pretty like easily, like in a straightforward manner. But then, of course, if you try to recognize what the distribution, the full conditional posterior distribution for each of the parameters, like beta 0, beta 1, and there's 1 over sigma squared, is going to be more involved. We're not going to cover it, and we're going to rely on JAX to perform the MCMC for us. Okay. But yeah, I just want to show that you can still write out the joint likelihood, and then from there you can get the joint posterior. Nothing daunting. And you can imagine that later if we add more predictors, meaning that you're not going to have just xi, but you might have xi1, xi2, xi3, that's indicating like say 3 different predictors in there, then you're just going to keep adding them in there. And I should also mention, because some of you earlier, like at least at some point, because of your project, I asked some of you try to read half the textbook chapter 7. And that's on multivariate normal model. And I just want to mention that typically when you are trying to do derivation for the joint posterior, like whatever we see over here, I told you here that it's complicated if you're trying to do it like element by element in this case, okay? But what the usefulness of the multivariate normal model that some of you have heard about is that conventionally, the prior people use for beta and beta 0 and beta 1, or any other like beta 2, 3, 4, if you have more predictors. Typically, people do it as a joint multivariate normal distribution. Okay, so maybe just a quick detour. So multivariate normal, so we know that univariate is we have, say, whatever we have so far. Okay, so if you have univariate outcome, and then you assume, like giving a univariate normal data model, if you have multiple outcomes, which let's say yi1, yi1 and yi2. So say and typically we write it as a small vector. So that means for the same observation, I get, what kind of example can we use? Say in the data set, the CE data set that we have, we are looking at the outcome to be the log expenditure and then the predictor to be the log income, right? But sometimes you might want to model them together. So this means for each observation, you have their log expenditure as well as log income. And if I want to model them together, I would do something like what I write over here, the multivariate normal, that I have two variables jointly following so here I will write multivariate normal MVN, and then you will see that the mean becomes a vector, say mu1 and mu2, and the standard deviation, which is not univariate anymore, it's going to be a matrix, 2 by 2 matrix, and typically you write like sigma 1 squared, sigma 1 2, sigma 2 1, and sigma 2 squared. Okay. Anyway, I'm only mentioning this because conventionally, when people are doing any kind of Bayesian linear regression, whether it's simple or multiple linear regression, they like to put multivariate normal prior for all of the betas together, right? And that actually can simplify the derivation much more, as long as you're familiar with all those matrix multiplication and all that, okay? But we're not going to cover this. Like what you can see now, I'm assuming all of the regression coefficients as well as the sigma, which is the standard deviation parameter, I assume them to be independent, right? And then I start to give univariate prior for them. So that a lot of times works just fine because you don't have a lot of information about, say, where the regression coefficient should be or how large the standard deviation should be. So we just put everything univariately and independently. But in the past, people do like to model, like say, all of the betas together using a large multivariate normal distribution. So they're able to capture, say, any kind of dependence among those beta 0 and beta 1 and beta 2 and beta 3. Okay? We're not doing that at all because at first, in the prior, we already assume that they're independent. Okay? Anyway, both at good and bad, but just so you know that, well, maybe in the future, if you ever get into this again in a graduate level course or in your workforce, the multivariate normal is still very useful in the regression setting. Yeah. All right, so, but for us, we're gonna do JAX, so everything will be simpler.